Okay, we're going to look at limits and continuity as it is discussed in calculus. And if you are a random passerby on the internet and you want a hard copy of the problems that are in this video, you can go to bit.ly/limitcont and print that off. It may help you in taking notes. So let's talk about limits and continuity as they're defined in calculus. First, let's get the definition of continuity. And it is that if a function f is continuous at x equals c, or the function f is continuous at x equals c, if and only if, and this first parentheses, the shorthand for if and only if is IFF. So you may see me use that a lot in the future. So IFF is if and only if. So a function is continuous at x equals c if and only if the limit as x approaches c of f of x is equal to f of c. So if you're asked to justify or prove that a function is continuous in calculus, this is what we will do. So let's look at it graphically and explain what that means. First, if the limit exists, that means that the limit as x approaches c from the left of f of x must equal the limit as x approaches c from the right of f of x. And in order for that to happen, so as we're coming to c, that just means as I come from the left and I come from the right, we have to be going towards that same spot. But the limit existing is not enough to prove continuity, because without this last piece, it is possible to have an existing limit and still have a removable discontinuity. And so the way we guarantee continuity is we make sure that we fill in that potential hole with the function's actual value, f of c. And so if f of c is equal to what the limit is, then we effectively plug in that hole and we have an existing limit. And they do need to equal a finite number. So if all of them are going to infinity or something like that, then that would not be continuous. So let's put this in practice. Move my head. So we're going to determine whether or not the following functions are continuous at the given value of c. And if they are discontinuous, we need to state the type of discontinuity. So the first one's going to be really easy. If you're just given a regular function, an irregular, I don't know if that's really defined, but we just have a rational expression here. Let's start by just trying to plug in 9. So if I do f of 9, you will see that f of 9 is equal to 12 divided by 0, which is undefined. Since f of 9 does not exist, then it's impossible for the function to be continuous. So therefore, f is not continuous at x equals 9. And as far as the type of discontinuity, I'm not even going to use calculus on this one, or not the limit approach anyway. In pre-cal and algebra 2, you should have learned that if your denominator is equal to 0 and it does not cancel with something in the numerator, this is a vertical asymptote. So we have a vertical asymptote / infinite discontinuity at x equals 9. And all the rest of the problems we're going to look at, actually, we will need to look at it from a limit approach. So let's look at number 2 here. And these are the type of problems that typically ask you about continuities when you have a piecewise function. And so we need to, in order for this function to be continuous at the x value of 2, then we need to show that the limit as x approaches 2 of f of x is actually equal to f of 2. And if we look at the limit, we can see that the left and right sides of 2 are defined by different equations. So I will have to analyze left and right sides separately. And then I have to compare that to the value of f of 2. Okay, so my left side of 2 is up here. And so I'll do 2 plus 5, and that is 7. My right side down here is 2 squared, which is 4. I'll write 2 squared. 2 squared plus 3, that is also 7. And so I know that the limit as x approaches 2 of f of x is equal to 7, but that does not guarantee continuity. We could still have a removable discontinuity, so we make sure that we do not have that removable. So f of 2, and f of 2 is when x is equal to 2, so that's also going to be 2 plus 5. That is 7. Now I can say that that is also equal to f of 2. Therefore, that's a jacked up therefore. Therefore, f of x is indeed continuous at x is equal to 2. And you do have to, I know the arithmetic that you use to solve the left-hand limit is the exact same as the arithmetic you use to solve f of 2, but you do have to write that down. If you do not write down f of 2 equals 7, then you have not proven continuity. So make sure you go through all three of these. And let's look at number 3. Same situation. We have a piecewise function that I'm curious about when x is equal to 1 or c equals 1. So I'm going to do the limit as x approaches 1 from the left. Left side is 1 cubed minus 3, that's negative 2. The limit as x approaches 1 from the right side of 1 is down here, that'll be 5 times 1 minus 7, that's also negative 2. So my limit exists. However, f of 1, that's when x is equal to 1, and at 1, my function has a value of 0. And so I can now say that the limit as x approaches 1 of f of x is not, well, I'll say this, it is equal to negative 2, which is not equal to f of 1. And that therefore the function is not continuous. Now, as far as the type of discontinuity, what we have shown, if you look at this graphically, as we approach 1, so here's x equals 1, we know the limit is negative 2. So that means my left side and my right side are coming in at negative 2. However, f of 1 is 0. So we have a redefined point up here on the x-axis, and that is a removable discontinuity. Removable discontinuity. Is there supposed to be an either? I don't think so. Removable discontinuity at x is equal to 2. Pretty good there. Cool. All right, let's move on to number 4. Another piecewise function with a lovely trig in here. So we are curious about x equals pi over 3. My left and right sides of pi over 3 are different equations. So once again, the limit as x approaches pi over 3 from the left of f of x is going to be the sine of pi over 3. And I fully expect my students to be able to do that without a calculator. You need to know that unit circle. Pi over 3 is up here. Your sine is going to be root 3 over 2. Then I need the limit as x approaches pi over 3. That should be a 3 right here, root 2. Pi over 3 from the right is going to be 3 times pi over 3 minus 4. That's pi minus 4. Okay, I don't know what that is, but I do know that it's not equal to root 3 over 2. Just to complete all of the components, I'm also going to find f of pi over 3. That is going to be the denominator, the bottom piece down here. And so that will also be pi minus 4. Okay, but I can see that my left hand and my right hand limits are not equal. And so really at that point, I already knew discontinuity. So the limit as x approaches pi over 3 from the left of f of x is not equal to the limit as x approaches pi over 3 from the right. And if the left and right side limits exist, yet they are not equal, that creates a jump discontinuity. So we have a jump discontinuity at x equals pi over 3. Left and right sides are going to different places. There is your jump. And then there is one more type of question that I wanted to look at here. And this is what they call removing discontinuities in the AP Cal curriculum. And so what we're going to do here is we're going to make this function continuous at x equals 4. And we have to do that by changing the value or determining the value of a that makes that happen. So we're really going to do the same thing. And it does say justify. So I'm going to go through the full limit approach of this. So the limit as x approaches 4 from the left of f of x would equal 3 times 4 minus a. We don't know a yet, so we just have 12 minus a. Then I need to do the limit as x approaches 4 from the right, which will be 4 squared plus 1, that is 17. And then I also need f of 4, and f of 4 is that bottom piece. That's also 4 squared plus 1, which is 17. And in order for this function to be continuous, I need all of these to be equal. And so I'm going to set these, it really doesn't matter which two you pick, but I need 12 minus a to equal 17. 12 minus a would equal 17 when a is -5. So there is your value of a that makes this function continuous. And then just as a final statement, I'm going to say that if, or maybe for a equals -5, the limit as x approaches 4 of f of x would equal f of 4, and they all would equal 17. So I'm going to write that final conclusive statement to establish that we are indeed continuous for the value of a equals -5. And then one more same thing. Show that this function f is continuous at x equals 4, and we have to determine the value of a that makes that happen. So the limit as x approaches 4 from the left, 4 from the left of f of x would be a times 4 minus a squared. Limit as x approaches 4 from the right of f of x is 2 times 4 minus 5. That is 3. And then f of 4 is, again, that top piece, which we have the a's in. So that would be 4a minus a squared. And in order for this function to be continuous, all of these have to equal each other. So I'm just going to take any two of these a expressions, or they're the same thing. I'm going to take the a expression, set it equal to 3, and channel my algebra skills. So let's see, I'm going to factor this one. 0 equals a squared minus 4a plus 3. That factors 2, a minus 1, a minus 4. And we get a is equal to 1, and a is equal to 4. And there are actually two values of a that will make this function continuous. And I'm going to make that conclusive statement again. F is continuous at x equals 4 if a is equal to 1 or, move my head, a is equal to 4, because the limit as x approaches 4 of f of x for those two values of a would equal f of 4, and they would all equal 3. If you want to test it, the two values of a is a little bit scary, so if you want to plug in 1, 4 times 1 minus 1 squared is indeed 3. And if you plug in the other value, 4 times 4 is 16. Uh-oh. There's an error. Whoops. And that's why you check your answers. This is why you check your answers. So I was plugging in 1 and 4 to make sure that both of these did indeed equal 4 or 3. And I now realize that that needs to be minus 3. Let's fix all this. So 4a is equal to 3 would be the other one. There we go. 3, 3, 3, and let's test the 3 now. 4 times 3 is 12, minus 3 squared is 9, so 12 minus 9 is indeed 3. So there we go. That worked out, and I'm glad I checked my answer on that very last one. So there we go. Hopefully that makes some sense.